Ah, that is excellent. Okay, well, thank you so much for that comprehensive introduction. This is indeed the presentation about Espressif RiscV developments. I have subtitled it towards multicore and more standardization, but we could have also called it, let's just see what Espressif has been up to these last 2 years. So as you already said, my name is Jeroen Domburg. I'm a senior software and technical marketing manager. I also do hardware stuff, architecture, a little bit of everything within Espressif. About Espressif, you already kindly mentioned the main points there. So we are in the business of AIoT, which is a contraction of AI, artificial intelligence, and IoT, Internet of Things. We started out doing Internet of Things chips, so chips that you put in little devices and widgets that connect to the internet somehow, mostly via Wi-Fi initially. But we're now also making headways into the AI bit, especially edge AI is getting more and more important. So we also make chips that can do that and develop software solutions for that as well. We're a fabless chip company. That means that we do everything up to the actual manufacturing of the silicon in-house. So we make the designs, we design the IP, we do the tape out, etc. But the actual manufacturing of chips we leave to TSMC. They're way better than us at that. We are headquartered in Shanghai, in China. But nowadays we are more or less a multinational company. We have offices all over the world, multiple in China. We have a research office in India. We design a bunch of software in Czech. Nowadays I'm stationed in Singapore. We have a bunch of people in Brazil doing interesting stuff. So back in 2021, I already presented at the RiscV days before. That was in spring. And what I did there is talked about the ESP32C3, which was a chip that we had just introduced or were about to introduce. I'm not sure anymore. The specific reason I wanted to talk about that was that is our first chip that used a RiscV architecture CPU as the main CPU. And in this case, it ran at a nice 160 megahertz. It also, as I said, we're an IoT company, so it needs connectivity. And in this case, this chip has Wi-Fi and Bluetooth low energy as radios to connect to the outside world. A few more specs, 400K of RAM. We have a bunch of peripherals in there. I'll show you a bit more later. And one of the reasons I thought it would be interesting to talk about it was that we did some things differently, because this is not a chip that is, this is not our first chip. We actually have a lineage of other chips that we can also import things from. So since then, a lot of support has appeared. People seem to really like the chip. So ESP-IDF, which is our own SDK, obviously supported it very early on. Arduino followed soon after, so you could write your Arduino stuff and target it at ESP32C3. But also other things, for instance, Rust support also popped up pretty quickly, up to no standard lib support as well, as they call it. Notix and Zephyr are two very well-renowned open source real-time operating systems. They also supported it pretty quickly. And a bunch of other ecosystems as well. Toit, which is a new language, ESP Home, which is a framework, and there's a whole bunch of other ones that fairly quickly took up support for the ESP32C3. So also people wrote books about it. Elector wanted to write a book about the RiscV ISA, specifically assembly language programming. And they were nice enough to use the ESP32C3 as their main target, actual silicon target for it. On the topic of books, we also released a book ourselves, which uses the ESP32C3 as a vehicle to learn how to program IoT devices. A little bit of a plug here. This book is actually a free download. If you put this into Google, you'll get the PDF from our official site. So if you want to learn more about this, you can just read through the entire book freely if you want to. Okay, one of the things that I mentioned back in 2021 is that one of the reasons that we might want to do this is because of cost improvements. And while I don't have the internal numbers for it that I can release, I can give an example on this. So this is our previous chip. This is an ESP8266 based chip, has an extensor core, has a few peripherals, UART, GPIO, SPI, and that's it. Has a little bit of memory, I think 200K or something, and only has Wi-Fi. And if you go to the Mouser website, you pay $1.20 for it. This is an ESP32C3 based chip. It has Wi-Fi, BLE, it has twice the amount of RAM, it has a whole bunch of peripherals, and you pay an additional 4 cents for that. So I would say that has panned out. If you think those 4 cents still is too much, for instance, you can live with a lower amount of RAM and less peripherals. Then we also have the ESP32C2, which is a stripped down version of the ESP32C3, which is very useful if you want to make, for instance, wireless light bulbs that don't really need that many peripherals. I couldn't find like a real world market costs for that very quickly, but if you buy these in large amount, it will cost you about 50 cents or so, I believe. So it's fairly cost optimized. So I would say that we had a great success there, and a lot of places start using the C3 or its little brother, the C2, as a replacement for the ESP8266, which is great because people can do more interesting things with it for lower cost. I mean, that's great. So obviously, since the C3, we haven't just been sitting on our laurels doing nothing. We've actually been developing new products, and I'd like to introduce those to you now. Some of them are already there, you can buy them. Some of them are still in the engineering sample phase, and some of them haven't taped out yet. So the first of all I already mentioned is the ESP32C2. It's the cost down version of the C3. It still has all the radios, so you can still connect to it using Wi-Fi or BLE. But it only runs at 120 megahertz, which still is pretty fast. It has less RAM and a few less peripherals, and that makes it cheaper, obviously. And it's a pretty small chip. So here is actually a package that was broken down using ACID. And what you can see here is 2 chips. The top bit with the blue things on it is actually the flash chip. It's I think 2 megabytes of flash that is die bonded to the actual C2 chip, which is under that, which is not much bigger than the flash chip. So yeah, I think we succeeded in keeping it cheap and small. Another newcomer is the ESP32H2. This one is interesting because it does not have Wi-Fi. It is made for like consumer products, mesh networks. So it does have BLE as well as Zigbee, as well as the new Matter/Thread standard supports. So it is meant to go into devices that you put in your home that can interoperate using those standards. So it's not that fast. It's only 96 megahertz, and it only has 320K of RAM. But because it doesn't need to support the high throughput Wi-Fi protocols, it doesn't really need that. And finally, because also partially because we don't have Wi-Fi, it can be lower power as well. So then there's the ESP32C6, which is our first Wi-Fi 6 chip. Aside from that, we also put all the usual suspects and the new protocols in there. So it has Bluetooth Low Energy. It also has Zigbee and Matter and Thread. And Wi-Fi 6 is specifically interesting because Wi-Fi 6 added a bunch of features to the protocol that allow for lower power usage in chips. So in general, we also managed to make the power uses of this chip a bit better to control. So it is easy to make lower power devices with this that still connect to Wi-Fi, even without going into deep sleep or stuff like that. Aside from that, it's similar to the C3. The peripherals, the memory, etc., is pretty similar. The thing that we do have here is that we have given it a fairly fast 40 megahertz, I think, low power RISC-V coprocessor. And the trick is that when the entire chip is asleep, this thing can still wake up and do sensor readings or update a display or things like that, even while sipping power. Then we have the ESP32P4, which goes in an entirely different direction. First of all, it doesn't have any radio at all, so no Wi-Fi, no Zigbee, no BLE. But it does have a dual RISC-V core, and that is actually a high-power RISC-V core that is faster in CPU cycles, in instructions per megahertz than the other chips that we have. Aside from that, it also runs at a very high 400 megahertz. So yeah, it's a beast. It also has the low power RISC-V coprocessor. It has a bunch of video peripherals as well. We think that people want to use this for video-based things. So it also has a bunch more RAM, and you can actually also use the internal RAM as cache for a lot of external RAM as well. So this is quite the powerful beast. If you still want to have a radio in your device, what you can do is you can just take one of our C-series chips and put it in your project as a companion chip. So if you want to go cheap, you can put a C2 in there. If you want to have Wi-Fi 6, you can put a C6 in there, etc. So that's the way we're envisioning people to give connectivity to these things. Unfortunately, it's not out yet. We expect it to appear on the market. Well, I can't really give a hard timeline, but you'll see it appear at some point. So just in case you're interested what it looks like, so as a reference, this is the block diagram for the C3. So it has a bunch of peripherals, it has the RISC-V, etc., etc. If you keep the peripheral block in mind and compare that to the C2, then you can see it's actually stripped down by a fair bit. The H2, on the other hand, does have a few more peripherals, but in general, it is lower power, so a bunch of those peripherals can be shut down if you want to, and obviously it doesn't have Wi-Fi. And the C6 has all the peripherals again and includes Wi-Fi and all the other things, and also the low power coprocessor. Finally, the P4, which has a bunch of MIPI peripherals to attach cameras and displays and stuff. It has H.264. I think that is encoding, but I'm not sure. It has a JPEG codec and in there, so you have a bunch of hardware accelerated imagery stuff. For connectivity, as I said, it does not have Wi-Fi or any other radio protocol, but it does have Ethernet and USB high speed. So if you want to have a wired solution, this chip would be enough. Yeah, and aside from that, it has a whole slew of other general purpose peripherals. Okay. So I wanna dig a little bit deeper into the actual RISC-V core stuff because obviously this is a RISC-V conference. So we made a few improvements over the way we handled things earlier. So for instance, in the 2 years ago, one of the things that I said was with regards to interrupts that we took our own route. We effectively took the solution we had from the Extensa days and ported that to RISC-V. And that means that it's effectively fully custom. We're trying to get rid of that. So the C6 at least has a clint for local interrupts, so that confirms to the RISC-V specs. And for the P4, we just put a PLIC in there, which is entirely RISC-V compliant. So for RISC-V trace functionality, for the C3, it's very simple. It didn't have that. If you want to run a trace on the C3 core, you can't. For the 6, sorry. for the C6, the trace functionality was included, so you're now able to run a trace. And for the P4, we're going to implement the V2 standard of the trace RISC-V trace standard. So it's going to be even nicer. Also, all of these chips will have the same USB serial JTAG peripheral integrated that the C3 has. That means that in order to get at those traces or program the chip or have serial communications with it, all you need to do is connect a USB cable to the chip directly. You don't need a JTAG adapter or USB to serial or any of those shenanigans. The chip will just support it directly, which is really nice. And we've had a few good examples of people using that on the C3 very successfully. So another thing is the ESP32P3 actually is powerful enough to run Linux, which is great. We have a proof of concept in-house that can do that. However, while this is very nice, this is actually not production quality. It is a no MMU version of Linux. We don't really see this as the main target, and we're not sure if we're gonna properly support it. We think that it's better to program these things in ESP IDF or NUTX or any of the other MCU-ish programming environments. So we also have a bunch of extra instructions. We call them AI instructions. They're mostly a holdover from the ESP32S3, which is Extensa based. We added a bunch of instructions in there, and we effectively ported those to the P4. And again, the fact that it's RISC-V is really helpful there, because there's just places in the instruction encoding where we can put those instructions and not get in the way with anyone else. So those AI instructions are, it's mostly SIMD instructions. There's a few FFT instructions and some fast GPIO instructions as well. So that is what that contains. We call them AI instructions because we envision them mostly being used for AI stuff. So the final bit is what we learned from doing the C3 thing, and why the improvements that I just mentioned are there. So first of all, about the transition from Extensa to RISC-V, we actually got a performance improvement out of that. That is not to say that any Extensa core will perform lower than any RISC-V core. I mean, it is obviously also very dependent on the types of cores that we have. But in general, we find that for the same amount of silicon, at the RISC-V cores that we obviously optimized perform a bit better than the Extensa cores. So that is very nice. We also found that it was easier to add features. The Extensa core is the Extensa cores that we used are a bit opaque. The RISC-V cores we maintain ourselves, so we have all the source code, so it gets a lot easier to add features. You don't have to work around places that you can't see. And as I said before, it turns out it's cheaper. So from here on, it is very, very likely that we won't be releasing any Extensa chips anymore, and that all the next chips that we'll release will be RISC-V. On the side of software support, migration is pretty easy, actually. All you need to do is take your SDK, and if it's written in C or C++ or any high-level language, you just need to add support for the lower-level devices that change, say, interrupt APIs, etc. But aside from that, everything on top of that is just C and just keeps on running. So our users have had very little difference. At least in ESP IDF, I know that you can just take your old project that was written for an ESP32 that used an Extensa core, and you can just change the target to RISC-V, recompile everything, and there's a high likelihood that everything will just work. What we did find was that RISC-V attracts support for other languages and operating systems and SDKs and stuff. seemingly a lot of external projects that we didn't maintain were like, oh, they have a RISC-V chip. RISC-V is actually something that is going to be big and is open source, etc. So they were more interested in adding support for our RISC-V chips than for our Extensa chips. Extensa chips are still seen as a little bit proprietary. We only have a GCC version that we mostly maintain ourselves. There used to not be an LLM version for it, so the compiler situation is a bit precarious. For RISC-V, everyone is just like, yeah, it's all there. Why shouldn't we add support for it? So that's a very nice thing to have. About the custom stuff that we implemented. So the interrupt controller. Initially, I think a few projects were a bit hesitant on how to implement like custom stuff for interrupt controller. But nowadays that source code is in there. So if we were to stick to that, it probably wouldn't be a big problem for existing projects. However, we do agree that more standardization is better. Also, because if there's new projects that want to make use of the C3, for instance, then they still need to, write a custom code for a custom interrupt controller. While if it's a standard click or PLIC or whatever, then you just reuse the code you have for other RISC-V chips. So the other thing that we still have custom is the AI instruction set. So the AI instruction set is more or less a 128-bit SIMD instruction set. And as I said before, it also has some FFT and fast GPIO instructions. So is it a good idea to still add a fully custom instruction set to our new RISC-V chip? Well, on one hand, we have the fact that we are compatible with the S3 and we can make use of the libraries and tools that are already written for the AI instruction set in the S3. On the other hand, there's also the upcoming P extension to RISC-V, which also does a bunch of SIMD stuff. Wouldn't it be better to implement that? And the answer is maybe. That standard is not fully ratified yet, if I recall correctly. So there's a thing. But the other thing is we're talking about instructions now, and RISC-V is extendable. So if we want to in the next chip, we can just implement both, have both support for our custom instruction set as well as for a ratified P extension set. We're not entirely sure how that will go. So that is still something that maybe the next time I speak here, I will go into. We'll see. So that is the end already. I have no idea where I am on time, but I don't have any more slides. So thank you very much for listening. This is my email address and our website. If you have any questions, I'd be happy to answer them.
Okay, thank you, Mr. Domburg. So do you hear my voice?
Yes, I hear you.
Okay, so the presentation is open for the questions. So any question, comments? So while audience is thinking, so let me ask one very open questions. So what do you think about kind of enhancements for AI? So there are many, probably several ways. So extend that it's 5x extraction.
Enhancements for AI?
Yes, or some putting on some AI accelerator or other things. Would you comment on that?
Yeah, so we do think that it'll get more and more important. As I said, edge AI, which is the use of artificial intelligence in your endpoint devices, so in your widgets itself, rather than a widget just being a pipe that sends whatever it needs to process to a server somewhere that then does the processing, voice assistants like Alexa do that at this point. We do think that actually processing sensor input and stuff like that inside the device will get more and more important. So what we want to do is give people the performance in order to build stuff that can do that. And you can already see that for the S3 that we do have a bunch of people who try to make examples where it's useful to have local AI. One of the things I don't recall who made it, unfortunately, but one of the things that comes to mind is, for instance, a glass breaking sensor. Nowadays they tend to use very crude algorithms, but you could actually use machine learning on that and have a better glass breaking sensor by just teaching it what breaking glass looks like. And obviously, if you have a glass breaking sensor, you don't want to send every single noise you hear up to a server in order to process it to see if there's a break-in. You want to process that locally on your device. And I think accelerated AI, specifically in hardware, will help a lot there in order to keep costs down and also energy consumption down, because obviously hardware acceleration tends to be more energy efficient than doing things in software. Does that answer your question?
Yes, partially, yes. So any other questions? So time schedule comes. So I'd like to thank you, Mr. Jeroen Domburg. Thank you very much for the remote presentation. So thank you. Bye-bye.
Bye-bye.
So